Hello, everyone, and welcome to today's webinar, Scattergraph Principles and Practice. This webinar is part one of a multi-part series. In today's session, we'll cover the fundamentals of scattergraphs. My name is Eric Lott. I'm the marketing manager here at ADS, and I'll be serving as your host today. Today's speaker is Kevin Enfinger. Kevin is a product manager at ADS with 25 years of experience in environmental engineering and consulting. He's worked as a project manager, project engineer, region engineer, and most recently as product manager for us here at ADS. Kevin is a registered professional engineer in 6 states, a member of the American Society of Civil Engineers and the Water Environment Federation. He's authored numerous technical papers and presented numerous presentations through these organizations to advance the science of wastewater collection systems evaluation. So thank you, Kevin, for your ongoing contribution to our industry, for all you do for our company, and especially today for the time and effort in preparing the information for this webinar. So without any further introduction, Kevin, we'll turn it over to you.
All right, thank you very much, Eric, and thank you everyone for joining us today. So the overall purpose of this particular series is to help you learn how to use scattergraphs. And when we talk about scattergraphs, we are talking specifically about scattergraphs, flow depth, and flow velocity data from sewer flow monitors. And we want to use these to understand various flow conditions that are observed in what I call the urban sewer environment. In particular, we're going to focus on 2 key questions. What do these tell us, and what are their implications? Before we do that, I want to provide a little bit of background just to make sure everybody's on the same starting point. When we talk about measuring flows in sewers, we do so by something called the area velocity method. So almost any make or model of sewer flow monitor that you look at for gravity sewers operates on this principle. And the principle works like this. If you have a partially full sewer and it's flowing, as in this example, from left to right, you can slice a cross-section through that sewer. And that cross-section has what we call a wetted area, and that is the area that's taken up by the actual flow in the sewer, and that cross-section is moving at a certain average velocity. So if you take that area times that velocity, you get a flow rate. That's the area velocity method.
Go get a yogurt tube out of the refrigerator.
The basic principle of operation on which all of these flow monitors operate. So here's the equation. Q is equal to AV. That's how we typically represent it. I'm showing here the units in like we've used them in the U.S., but obviously they would be different for any of you watching internationally. All right, so when most of us think about flow monitor data, we think about it like I'm showing you here. So we measure the depth, we measure the velocity, and we calculate the flow rate. And often that is presented in a time series plot of any one of those data points or any combination of those data points. In our industry, we refer to this type of graph as a hydrograph. And most of us can very intuitively understand a hydrograph. It's simply what comes down the pipe and when. It's a good way to think about a hydrograph. However, there's another way to think about this information. We can take this depth data and this velocity data, and we can plot it together on something called a scattergraph. I'm showing you here a scattergraph where the depth is plotted on the y-axis and the velocity is plotted on the x-axis. Now, mathematically, we all understand what a scattergraph is. It's just one variable plotted against another. And we use this to see if there's, or investigate some kind of trend. So initially, when we first started using scattergraphs at ADS, this is really what we were using them for, as a QA/QC tool to understand, do we have good repeatable data? Now, the one thing that we also need to understand is we need some perspective on this data. With a hydrograph, that perspective is that diurnal pattern that we expect to see. Well, what is that default expectation for a scattergraph? Well, it turns out that default expectation is the Manning equation. So I plotted that here on top of this data, and all at once you can now see that not only do we have some consistent data in terms of depth and velocity relating to each other, but it also follows a pattern that we might expect it to follow in a sewer. So that's a good thing. We automatically get some extra grounding, some extra framework on this data. So the Manning equation turns out to be very important for understanding scattergraphs. Now, because of that, let's go talk about the Manning equation in a little bit more detail. So looking at the registered list for this webinar, I would venture to say 80 to 90% of you on this webinar today have either a civil or an environmental engineering background. And so as such, most of you are very, very familiar from the Manning equation. You should have seen it in your undergraduate engineering days. However, I find that when we use the Manning equation on scattergraphs, people tend to get a little confused a bit. And so I always like to take the opportunity to go back to the Manning equation, go back to your college days, if you will, and let's get on some familiar ground, and then we can proceed from there. So the Manning equation, of course, is an empirical formula, and it simply defines a relationship between depth and velocity. It does so under specific conditions that we call uniform flow conditions, and this equation is commonly used to design sewers. Now, in a design mode, a civil engineer is often having to make many assumptions about flow rates they're expecting a pipe to service, and then they're making some assumptions about what the flow conditions will be like. One of those is often uniform flow conditions. Now, when we have existing sewers that we are evaluating, I like to say we almost operate in a reverse engineering mode. Instead of making assumptions and designing something to fit those assumptions, we're actually taking measurements of an existing system that's already in place, and then we're using engineering principles to look at that data and investigate what that data means. So, but nonetheless, the Manning equation is a very important equation that we use. So that equation is here. Again, for my international listeners, this is not the same equation you would be using. In the U.S., we would use 1.486 in this Manning equation. In a metric version, that number just changes to 1. So it is units dependent. But there are some common parameters here we're going to talk about. We have the velocity, we have the roughness coefficient, something called the hydraulic radius, and then we have a slope. I have it referred to here as a slope at the beginning. Let's talk about the roughness coefficient. So the roughness coefficient represents the internal roughness of the pipe wall, and it's a function of the pipe material and condition. And if you look at this in this equation here, the roughness coefficient is referred to as N. If the roughness goes up, as you might intuitively expect, it's harder for water to get through that pipe. So the velocity correspondingly goes down. Likewise, if you have a smoother pipe, water is able to get through that pipe easier, and the velocity goes up. Now, when we are using the roughness coefficient in the design mode, the common number you'll see is 0.013. I'm going to ask everybody real quick if you can mute your phone or double check and make sure your phone is muted. Thank you. The most common value for this parameter is 0.013, and you'll often see a range of maybe 0.009 all the way to 0.017. You start to get out of that range, then you're starting to deal with things like natural channels and things like that, not those that you typically find in the urban sewer environment. Let's talk about the hydraulic radius. So I'm showing you a diagram here on the left that represents flow in the cross-section of sewer. And when we talk about the hydraulic radius, it is a definition. It is defined as the ratio of the wetted area to the wetted perimeter. We already talked about what the wetted area is, and the wetted perimeter is simply the contact that the flow makes with the pipe wall. So you figure out the geometry there and do that math, and you have something called the hydraulic radius. And once the pipe size and shape are established, and those are considered fixed, basically the hydraulic radius is simply a function of flow depth. And that's where depth enters this Manning equation. Now, the last piece of the Manning equation is the slope. And for anybody that's used the Manning equation in a design mode, we often think of this as the slope of a pipe. In reality, it represents the slope of the energy gradient, or the hydraulic grade line, which, under uniform flow conditions, is parallel to the slope of the pipe. In other words, the two are equal. So that's an assumption that's typically made with the Manning equation. I think a lot of us tend to forget that at times. But it's an important distinction to remember. Now, we talk about uniform flow here. What is uniform flow exactly? So here I've got an example. It's a profile view of a pipe. The flow is moving from left to right, upstream to downstream. And what you see is a representation of uniform flow. So when you have uniform flow conditions, the Manning equation in its traditional sense applies. And you can think about that equation and the graphing of that equation equating to this physical condition actually going on in a pipe. So I find one of the things that helps people when we're looking at scattergraphs of flow monitor data is if you can picture what that data looks like from a side profile in a pipe based on what you're seeing on a graph, you're going to have a good fundamental understanding of what's going on in that pipe. So let's get back to a graphical view, and we're going to start with this Manning equation as our fundamental principle, and we're going to do what I call build a better view of flow monitor data. So if we take that Manning equation and we plot that equation, we get something like this. And this is really a good fundamental point for civil engineers, environmental engineers, and the like to start their understanding and learning of scattergraphs of flow monitor data. Because most of you have seen this equation plotted just like this in one of your undergraduate engineering textbooks. So you can pull almost any of them off the shelf today, flip through the index, and quickly find a graph like this. It's often referred to as a hydraulic elements curve. The only difference here is you have the depth represented as a percentage or a depth to diameter ratio, and you have the velocity represented as a percentage of the partially full velocity compared to the full pipe velocity. Now, I'm going to make a few changes to this graph to provide something that I call physical perspective and context. It's actually going to help us understand the data a little bit better. So, watch with me here. I'm going to pull this left axis out, and then I'm going to drop in a cross-section of the sewer pipe. Now, this is not something that you see as much on graphs today, modern hydraulic textbook. But if you go back to some of the textbooks, say in the early 20th century, you actually find this feature on a lot of them they use for the Manning equation. Now, the reason for that is if you think about the early 20th century, a lot of the pipes that were being designed and built were some of the larger sewers in some of the larger cities, and they were built using a lot of different cross-sections. So you think other cross-sections, non-circular sections like egg-shaped pipes, horseshoe or basket handle, there's a whole variety of those. So you would often find a group of hydraulic elements curves in these textbooks that would show how the Manning equation changed with different pipe cross-sections. I actually like that. It helps show the physical context of that pipe. It also allows us to basically at a glance see where the depth is in relation to the pipe diameter. And we also add some graphics here to indicate flow moving down the pipe and to indicate the velocity moving from left to right in a way down the pipe. And then a big change that we have to add for scattergraphs, we need to add some graph space above full pipe. Now, when we're designing new sewers, we don't typically worry about this because we expect all the flow to be within the pipe. However, we recognize that many times, particularly during rainfall events or blockage events or things like that, these pipes will indeed surcharge. And so I need a place to show that data. I can do that like this. So basically, we've taken a basic hydraulic elements curve, added a little bit of physical perspective to it, and now we're prepared to add some data to this. So now instead of being depth to diameter ratios and velocities that are based on a full pipe velocity, I'm just showing you absolute numbers here. So you're looking at a scattergraph of a 30-inch diameter circular sewer, and you see the actual velocities plotted on here. And right off the bat, you see the fact that we have this data is in good agreement with the Manning equation. You also look off to the left, and you can tell that our minimum depths are around 5 inches, and our maximum depths are around 15 inches. So we start to get a lot of context and a lot of information about what's going on here in this pipe. Now, this is just a snapshot of this sewer in dry weather. If I add some data from a wet weather event, I get this. And there's actually quite a bit of information packed in here. We're not going to cover all of this information today, but we will over the course of several webinars. But just in this pipe alone, I can tell you that this is a 30-inch circular sewer, and that up until about 15 inches, I have uniform flow conditions in this pipe. Above that, this pipe goes into backwater and surcharge conditions, and at about 65 inches, it results in a sanitary sewer overflow, or an SSO, that occurs downstream of this location. I can also tell you that in the course of normal flows at this site, that this site exhibits good self-cleansing behavior. So that, at a glance, is quite a bit of information that comes out of this scattergraph. Now, we talked about earlier how the hydrograph tells you what comes down the pipe and when. A good way to think about a scattergraph is it tells you how that pipe handles that flow. So in this case, I've got one that does well in dry weather conditions, but because of something downstream, it goes into backwater surcharge, and we even see an overflow downstream. And that's quite a bit of information there. It's harder to see on a hydrograph. So with that in mind, I want to talk about how we use the Manning equation on a scattergraph. And it turns out there are 3 different methods that we use today to display a Manning equation on a scattergraph. And I have termed them the design method, the Lanphier-Cole method, and the Stevens-Schutzbach method. We're going to talk a little bit about each one today. Now, to really understand these methods, we have to rearrange the Manning equation a little bit. So I'm going to apologize on one hand, but I'm not going to apologize on the other for showing you a few equations today. So on the left here, you have the traditional version of the Manning equation. So V equals 1.486 over N, R to the 2/3, S to the 1/2. I want us to rearrange this equation just a little bit. And I want us to take the roughness coefficient and the pipe slope that we usually think of as being constant, and I want us to put them together. So that middle equation you see, you'll notice that I have lumped together in the middle of that equation the pipe slope and the roughness coefficient. And then I can define them as one parameter. We'll call it a hydraulic coefficient. I call it C here. For people that have that work at ADS or have been around ADS for many years, another term for this has been the hydraulic coefficient, or HC, we've used before. But think of that as just one parameter, and then I substitute that in to this third equation on the far right. So V equals 1.486 C times R to the 2/3. And what we do with that, we'll talk about as we go along. Let's take a look at the design method here. So this happens to be data from a 30-inch sewer. This one is in California. And what we've done is we've taken what I call the design method, which is how most of you understand the Manning equation. I've taken a roughness value that we've assumed, which is 0.013, and I have taken the as-built or design slope for this pipe, which happens to be 0.45% on this pipe, and I've used that to create the Manning or define the Manning equation and plot it on a scatter graph. Then I've taken the data from this location from a flow monitor, I've dropped it onto this scatter graph as well. And what we do with the design method is we simply compare the two. Do they agree or do they not agree? In this case, they happen to agree. And what that tells us is that this location, as it currently exists and operates, is functioning under uniform flow conditions, and it's functioning as designed. And this is really the ideal case. The best expectation that you can ever get out of a pipe is that it performs as designed. Because if it is performing as designed, it's performing to its best possible outcome. In other words, you're not going to get any more flow through this pipe, and you're not going to get any more flow through this pipe in a more efficient manner. Now, I mentioned earlier on, it's important when you're learning to understand scattergraphs and what they mean, is to associate the data on the graph with what that flow would look like if you could stand right beside that pipe and visualize a profile of flow moving through that pipe. So I've shown that on this graph here. And this is a classic example of uniform flow moving through a pipe at an ideal capacity. So this is called the design method, where you take your parameters for the Manning equation, draw your Manning curve, and then throw the data on the graph and let the data fall where the data falls, and the two will agree or disagree. In this case, they agree, and that tells us something very important about this pipe. Let's look at the next method. So this is something that I call the Lanphier-Cole method. And this was created by two gentlemen. One was named Kenneth Lanphier and John Cole. I believe they both used to work for the U.S. Geological Survey. This was a method they published in 1978. And what it does is it really takes the Manning equation and it operates it in reverse. So basically they were doing some work in some streams or channels, and they would actually go out and do a point measurement of depth and velocity, or get some profiles done. And they would say, okay, I have a depth and velocity data point. Let me draw a Manning equation through that data point. So they were basically doing this without having direct knowledge of the roughness or the slope of that channel. So basically we can take that approach, and instead of using it with one data point, we can actually do it with many data points and do a regression. So we can actually curve fit the data, or curve fit the Manning equation to the data, as long as that data is collected under uniform flow conditions. If so, you will get a very nice regression. So I'm showing you one here, and you can see where the data and the curve clearly agree, and the curve does a good job of representing the data that we have. So this tells us, in this case, without us having to know any knowledge of the slope or roughness of this pipe, we can fit a Manning curve through it. It tells us that we have uniform flow conditions. Again, you see that side profile up at the top. And then we can project the capacity on this pipe from that method. So the Lanphier-Cole method works well to curve fit the data that you have from a sewer flow monitor, but it only does that well if that data is gathered under uniform flow conditions. Now, we have another method at our disposal. We call it the Stevens-Schutzbach method. Now, these two gentlemen here they both work at ADS, so Patrick Stevens and Jim Schutzbach. I know many of you are probably on this webinar are probably familiar with Pat Stevens. You probably heard him speak many times before. And Jim Schutzbach is a longtime ADS employee that's worked in our research and development department for many years. They put their heads together and came up with this approach. And what they realized is that we had a number of sites that didn't operate under uniform flow conditions, but we still wanted to be able to define those with some type of Manning-related curve. It turns out many of those operate under something we call non-uniform flow conditions, and really this is a form of gradually varied flow or backwater conditions. Now, if you'll notice, there's actually 4 different curves plotted around this data. The curve on the far left, I'm going to point my cursor at it right here. So right here is basically us taking the Lanfear-Cole method and trying to fit it to this data. You'll notice it goes through the data, but it does a poor job of describing the data. Well, if we assume there's an obstruction downstream, this could be debris, it could be an offset joint, and we adjust the definition of the hydraulic radius a little bit, we have something that we call, this obstruction, we call it a dead dog. Pat Stevens came up with that term. Mathematically, I call it D sub dog. You see it represented here. But we can iterate that depth and take that into account. And you'll see each time we iterate that, we put a Manning curve through this data, and then we check to see how well it fits the data. If it doesn't fit well, we continue to increase the depth of that obstruction, and we continue to move it up until, lo and behold, you see we reach a point where we get a curve that very well defines this data. And you'll notice this R squared value, this is a statistical term here, on the goodness of fit. This R squared value is 0.95. That's an excellent fit on the data. Okay, so this here, take a look at this data. Now look above it to the profile that I'm giving you. So we're representing some type of backwater, non-uniform flow condition in this pipe. When you see that, you see this data does not point to 0, 0. You know that you've got some type of downstream condition that's causing you to have non-uniform flow conditions. Now, I wanted to show you one example where I actually compare all 3 of these methods head to head. This one also shows you a good example where data may not agree with the Manning equation as we traditionally know it, and that's okay. So what I did is I went back and looked at design drawings for this particular location. This one happens to be a 36-inch pipe in Tennessee. I assumed a roughness, and I used the as-built slope, and I drew this curve. And you can see it's way out here. It does not agree at all with this data. So the next thing I do is I take the Lanfear-Cole method. And I say, let me take the data I have and fit a Manning equation, assuming I have uniform flow to this data. You can see it goes right through the data, but it does a very poor job of describing that data. And the reason it doesn't describe that data well is because this data is not from uniform flow conditions. The data tells us there's a backwater condition present. So we use the Stevens-Schutzbach method. We get a nice fit here. And this brings out a really important point between these 2 methods right here. Notice the design method has a capacity right about here, so 3 feet per second at full pipe. The Stevens-Schutzbach method, under the conditions measured, tells us that we have a capacity of roughly 2 feet per second. So if you think about taking a pipe that's operating well, you know, think about throwing an obstruction in that pipe. The capacity of that pipe is going to be less. And this methodology shows that and illustrates that very clearly. So in this case, whatever condition is present in this pipe is causing us to lose about 1/3 of the capacity of this pipe. Turns out we had a field crew that went out to investigate this site, and it turns out that there was, I believe, some type of concrete or something like that that was built up in one of the downstream manholes. Once that was chipped away and removed, flow conditions returned to normal. And more importantly, the implication of that is that we reestablished the capacity of that pipe. So this is a good illustration here of the difference in these three methods, particularly when you have something like a non-uniform backwater type condition, which is actually not all that uncommon in sewers. I want to talk about one other minor point. I'm only going to bring it up on this one slide, is anytime we use the Manning equation, it's very typical for us to assume that the roughness coefficient is constant. In other words, it does not change as a function of depth. But one of the wastewater professionals of a past era, Thomas Camp in the 1940s, did a little research on this, and he concluded that the roughness coefficient does vary a bit as a function of flow depth. And he came up with a relationship for that. It's often described as Camp's varying roughness curve. There are some equations to approximate that, and there's some other researchers that have put out some information on that. These three methods that we've talked about today, the design method, the Landfair-Cole method, and the Stevens-Schutzbach method, they can all be adapted to use that varying roughness coefficient. I've shown that here on this particular slide. So I've taken the same data set, and then I have actually curve fitted the Manning equation to it in two ways. One with a constant roughness coefficient, one with a varying roughness coefficient. You can see the two do a great job of fitting the data within the region of the data. But the projections going up to full pipe, you can see, are a little bit different. In fact, they're about 20% different in this case. So it does have some implications that you need to be careful about when using this data, but both methods can be used. So I want to wind this down a little bit. So I want to talk about three key points that I want you to remember from this fundamentals presentation today. One is that scattergraphs of flow depth and velocity data, they are graphical tools that help provide insight into hydraulic conditions in sewers. So think about the hydrograph as telling us what comes down the pipe and when. Think about the scattergraph as telling us how that pipe handles that flow. And to help us understand that, it's important when we're looking at a scattergraph to understand what ideal flow conditions are like. That's expressed by the Manning equation. And it turns out that that equation is fundamental to understanding and interpreting scattergraphs. And that occurs, to be honest with you, whether you plot the Manning equation on the scattergraph or whether you just kind of implicitly visualize it on there while you're looking at the data. And what you're really looking for is when the data agree or disagree with the Manning equation. And then when it comes to using the Manning equation on the scattergraph, there's three methods in which it can be used. One is the design method. That's the one most of us are familiar with. And then if we have data and we want to curve fit the Manning equation to data, there's two approaches that we can use, the Landfair-Cole method and the Stevens-Schutzbach method. Now, there's no way in the world I'm going to present a lot of detailed information to you like this today without giving you a paper to reference and to learn the details in greater detail. So there are two papers that we have previously published. One is a paper that Hal Kimbrough and I published back in 2004. I know that paper sounds like it's a little dated, but I assure you every piece of information in that paper is just as relevant today as it was back then. I took great lengths in writing that paper back then because it was the way in which I learned how to understand these methods. So if you will take that paper and you want to understand the details of how to use these methods, that paper is there for that. This first paper is the one that discusses these three methods using a constant roughness coefficient. Later on, we investigated using these three methods with a varying roughness coefficient, and Jim Schutzbach and I paired up on that paper. And again, if you want to know the details of that, they are all there in great detail. I encourage you to check those out. They're actually on our ADS website. Now, I will also mention another important resource that we have available to you, something that we call the Scattergraph Principles and Practice poster. This is available in a high-res PDF format on our company website. So go to adsenv.com/scattergraph, and you can download a copy of this poster. And what I wanted to point out on here was that you can actually, or what we've actually talked about today, is really just the first row of examples on this poster. So we've talked about a lot of details today, and these are the fundamental details that you need. But this poster, for anybody that would like to use it, the very first example on the top left starts out with the Manning equation, puts you on that common footing, and each example builds greater detail and greater complexity until you get towards the end of the poster. So we've talked about some fundamentals today. I mentioned that we plan to do a multi-part webinar series to really give people a chance to understand scattergraphs and how to use them. The next topic I would like to discuss is going to be backwater and surge charge conditions. And we're going to talk about how those impact sewer capacity and how to identify those on scattergraphs. Some of the other topics I'm looking at after that are evaluating CSOs and SSOs, evaluating flow monitor performance, and for those that are interested, we have a few other topics after this that we can discuss if there is still good interest in these. So scattergraphs, actually, I'll give you a little backstory here. They're actually one of the things that brought me to ADS. I was intrigued years ago by what ADS was doing in this area. So it's been fundamental to what I've been doing at ADS for many years. And one of the fun things I have or enjoy about working at ADS is that I learn something new every day, and scattergraphs are something we've been learning something new about for many years, and we continue to learn more and apply them in new and interesting ways. So with that, Eric, I'm going to turn this back over to you, and we will field a few of the questions that we have had previously submitted.
Sounds good. Thank you, Kevin. We'll now move on to the Q&A time. As Kevin had mentioned, we have had a bunch of questions submitted during the registration and that were sent to me over email by the last few weeks. We'll only have time to address just those questions that were pre-submitted during today's call. Did notice a lot of chat that was going on during the webinar. I've captured all of the resources that were discussed. There's a couple of questions in there. And of course, we promised to follow up with you directly after the webinar to provide resources and to answer questions immediately as well. But let's go ahead and address the ones that were pre-submitted. The first question, Kevin, is, can you give us a brief history of the scattergraph?
Okay, so I actually consider myself to be kind of a student of the history of our industry. It's something I find fascinating. It's something I provide, to me, provides perspective on our industry. And that includes some of the graphs that we use as well. So I mentioned earlier that we've looked at these hydraulic elements curves from some of the early textbooks in the 20th century. That's where you start to see some of that information. Interestingly enough, we don't think of scattergraphs of flow data as being that old. But the first one I've actually found actually comes from the 1920s. It actually comes from 1924. It's a research publication where a professor was actually displaying some of his lab results. He was studying the flow of water in pipes in a laboratory setting, and the plot that he used is almost identical to some of the scattergraphs that we use today. So to that credit, I give to that professor. His name was Elgin Orozco Wilcox out of the University of Washington. In more of the modern element, really the first publication that I identified using sewer flow monitor data on a scattergraph goes back to 1987. And it's from a publication by the Water Research Center in the UK. It's called A Guide to Short-Term Flow Surveys of Sewer Systems. So ADS picked up on it from there and began using scattergraphs in the early 1990s. And we really haven't looked back since.
All right, question number 2. It's a two-part question, Kevin. You described the Manning equation as a fundamental component of the scattergraph, but what if Colebrook-White equation is favored in our country? Can it be used instead?
Okay, so that's for some of our international webinar participants. So in some parts of the world, the Manning equation is not used to design sewer systems. They prefer to use and are required to use something called the Colbert-White equation. And it essentially does the same thing. So yes, it can certainly be used instead of the Manning equation. Its parameters are a little bit different, and it's a little bit more complex to handle mathematically, but it can be used in the same role on a scatter graph as the Manning equation. So the answer is yes.
That's good. I love this third question. It is, will animation of scatter graphs be an option in the future?
Yeah, so animation is actually a really useful feature, and it allows us to see how data kind of emerges and evolves on a scatter graph. So if you think about a hydrograph, we have a semblance of time. There's a start and there's an end, and that tells us where that data occurs in time. When we take all that data and throw it on a scatter graph, well, time becomes invisible to us. We can't tell if one data point preceded another or not. So animation is a way to do that, and particularly animation in conjunction, with a scatter graph and a hydrograph paired together works really, really well to provide insight. We currently do that today on our existing splicer product, and we are looking to implement that in some other areas, but we do not have it implemented in those areas yet. So that's good to hear there's interest in that, and I'll kind of put on my product manager hat now and tell you that we do appreciate hearing about features that are desired or requested, and anytime we start to hear that from multiple users across multiple customers, that feature starts to rise up on our priority list of things that we want to get to sooner rather than later. So if you have features like that you're interested in seeing in ADS products, please let us know, because we do listen to those and we do use those to help guide what we do on our roadmap.
Okay, this next question is, a colleague of mine has the Scattergraph Principles and Practice poster hanging on her wall at the office. How can I get a copy?
Okay, so I mentioned this earlier. So I would say we have probably given out a few thousand copies of that poster over the years. We do see them on display on a regular basis at our customers' offices, and I'll tell you, we certainly appreciate that when we see those, because we know people find them useful and they're using them as a resource. At present, we don't have any additional hard copies in stock. So that means that your colleague has a collector's item on her hands for the moment. But as I mentioned earlier, you can download a high-res PDF copy to use. And for people that are interested in physical copies or a hard copy, I'll say if we have enough interest, maybe I can twist Eric's arm on his marketing budget. So let us know what kind of interest you have in those, and we'll take a look at that.
Well, you won't have to twist my arm very hard, Kevin. So, okay, let's make that our last question for today. Of course, we'd love to continue to receive your questions related to scattergraphs. So if you have a question or if you'd like additional information on what was covered today, you can email me. My email address is on the screen. I did notice some more good chat and some questions as we were going through these questions that were pre-submitted. So again, I've captured those, and we'll make sure to respond to those promptly. That is it for today. Again, thank you very much for your attendance, and this will conclude today's webinar.